Our journey on the chapter on fluids continues. All right, now we've looked at pressures at certain depths. We know the formula for pressure is rho GH. We've looked at buoyancy forces. We know the formula for buoyancy is rho GV. Okay, very nice. And now it's time to move on to another principle. Now this is called Pascal's principle. And I wrote it on the board. Pascal's principle states the pressure applied to a confined fluid increases the pressure throughout by the same amount. Now I drew an example here of a closed system. So you can consider these to be pipes of sorts, and then in the black areas are pistons. So when I see a piston like this, for example, I think of things like syringes. So when you push down on the syringe, the fluid is trapped underneath the actual piston itself, and then can be pushed outward. Now in the case of an injection, you might get an inoculation, a shot, a flu shot, whatever that is, something along those lines. But we see this principle in action in many other cases. So for example, you go to get your car repaired, a hydraulic lift, the things that they use to actually lift the car up, are utilizing this same principle. Bulldozer, to make the arms move back and forth. So they're closed systems filled with fluids, and fluids cannot be compressed. So if you think about the brake system on your car, that's a hydraulic system, very much like this. So once again, the principle says that the pressure, when you increase it, if I push down on this side, this piston, the pressure itself redistributes itself so that the pressure is equal everywhere in that closed system. All right, now let's take a look at it from the point of view of, since we know that the pressures are equal, I would say that the pressure that we put into the system has to be equal to the pressure that comes out. All right, now on this side we have a force pushing down on the piston, which creates some type of pressure. That's the pressure going in. So I'm going to use my hand and push down on that piston like so. Now the pressure changes and then re-equalizes itself. And you can kind of understand this. If the pressure is higher here, isn't it going to go to a place of lower pressure? So very quickly, things are rearranged so that the pressures are all equalized. If there were high or low spots, those would have a tendency to flow from high to low. Now the pressure on this side, of course, is equal, and we're going to call that pout. All right, so the pressure on this side we'll call pout, and it results in a force upward. So when we look here, we're going to end up with a force out. Fout. So here it is like this. All right, now we know a couple things about pressures. If the pressure that we have on this side is equal to the pressure on the other side, then we can check out to see what the actual forces are. All right, now we know that pressure is equal to the force divided by the area. So in the case of the pressure in, pin, all right, we're going to have the force, not just any force, but it's the force that's in. That's how hard we push with our hand. Divided by the area. What area? The area of the piston on the side that we pushed, put in, we'll call that A in. On this opposite side, we'll look here. Pout is the force, not just any force, it's the force out for pout. Now we have fout. Divided by the area, if we look here, the area out. All right, now let's take a couple examples here. Let's suppose that the force that I pushed inward with is, let's say, 20 newtons. Okay, if we look here, this piston is relatively small. So let's say the area of this piston is 0.03 square meters. So the area of the piston that's coming in is 0.03 square meters. That's still a pretty decent sized piston. All right, now on the opposite side, let's take a look and see what we get out of this. All right, now on the opposite side, the pressures have to be equal, so fin divided by in has to be equal to fout divided by A out. All right, now I'd like to know what the force is that I get out of that, so I'm going to leave that as my unknown fout. Now if you notice, the area of this piston, right here on the other side, A out, is much larger. So let's just make up something. How about 0.5 square meters? So on this side, you end up with 0.5 square meters. And voila, like this. We do a little multiplication, multiply 0.5 times 20, that's 10, divided by 0.03. Wow! Fout is going to be a relatively high number. So if we end up with that, we end up with this high force out. So Fout is much higher than the amount of force that I put in. Now this is important to us because as human beings we're very limited to how much forces we can apply. So we need to make machines that can do things like pick up automobiles, things that can dig like backhoes and diggers and things that bend things, and the jaws of life when they come to save you in the car. Those are all hydraulics. So when we put a little bit of force in, 20 newtons in, we're going to get large forces on the way out. So Fout is extremely high compared to how much force that we put in. This makes a mechanical advantage for us and makes us kind of like Superman and Superwoman.